Before we begin, did anybody have any questions on assignment 5 or 6? I pushed it back one more day and then I put up an announcement just for that stream that we talked about last time, just to work through assignment 3. Okay, don't see any questions yet. The last time we talked a little bit about recursion and we went through some examples of where you could use recursion, but they were mostly cases where it would be easier with like a for or a while loop, but we were just kind of doing it for the sake of getting a handle on recursion. Today I wanted to do one example really quick of a practical example of recursion where I think using recursion makes the problem easier than if you were to do it with a loop. And the problem I wanted to solve was Tower of Hanoi. And so we have like a little picture here. I'm sure a lot of you have seen this if you go to like a doctor's office. I know my high school math teacher had one of these where it's just like these rings and you're just supposed to move this stack of rings over to the peg on the far right. And so you're not allowed to move any rings below any ring that's bigger than it, or vice versa. You're not allowed to put a bigger ring on top of a smaller ring. So if I move like this one over to here and then try to move this one afterwards on top of it, then that's a no. So what I've done here is I drew up right before class started just an example of how we would solve this in the least amount of moves with 3 disks. So we have this small disk that's red, this medium disk that's blue, and then this other like big disk that's kind of turquoise-ish. And so the optimal solution to this is we move this red one over to the second disk, we move the blue one over to the middle, and then we move the red one on top of that one. So we end up with just this big one and then this stack of 2 on the middle. And then at that point, we're able to move the big disk over to the final place where it needs to go. And then we kind of just move the rest of them until we get there. So we move this one over to the first one, move the blue one over to the second column, and then we move this one over to the top. And then we have the tower again, except now it's on the second peg instead of the 0th one. So I've given them numbers here, 0, 1, and 2. And this is the optimal solution. And I've written out the moves we do. So we move from peg 0 to 2, 0 to 1, 2 to 1, etc. So hopefully everybody gets how this game works. I'm sure a lot of you have seen it before. But we can actually solve this pretty easily if we do recursion. And so if we can kind of consider what we did here is, in order to move the big disk, the one that's on the bottom of the tower, we need to move all the ones that are on top of it first in order to be able to move it to where it needs to go. And so you can see here in the first 3 moves, what we've done is we move the red and the blue kind of out of the way until they get to rod number 1, and then we're able to move this turquoise disk over to where it needs to go, which is the rod that it's going to be at when we're done here. And then afterwards, what we do is we basically just move these 2 that we moved off the top of it back on top of it. And so we gradually do that. You can see it's kind of the same as what we did up here, where we move the red to the far peg and then put the blue in the middle and move it over. Except its final position is just on top of the big disk. So really there's kind of 3 parts to how we do this. We move, so I'm going to split this up here. We move the smaller tower that was on top of it to the open peg. That's our first goal, is we want to move whatever's on top of our biggest disk to whatever peg we're not trying to move that big disk to. Then we move the big disk. And then we spend the rest of it just moving that smaller little tower with the 2 onto the big disk. So we kind of break it up into three things. And the reason I'm breaking it up this way is because we want to do this recursively. And so if you want to do something recursively or be able to solve it, we said that the kind of math definition is that you want to be able to break it down into a smaller problem or reduce it in some way such that it's a different kind of problem that we know how to solve. And so what we're doing here is we're reducing this first problem down to, can we move these first two disks off the big disk and move them to a different rod, which is kind of the same sort of problem that we were trying to solve, which is move an entire tower to a different rod, except the exception here is that we are moving a tower that is one smaller to a different rod, and being the rod that we're not trying to get it to, like the final goal. Right? And then the same sort of thing here, we're moving a smaller tower to the final rod that it needs to go to. And so these are smaller, I say smaller is kind of like quotation marks, but these are cases of our problem that are easier to solve, because if I try to solve just move two disks to one rod, then that's an easier problem to solve than the move three disks to a single rod problem is. And we are actually going to reduce that. You'll see in our solution here, the move two disks to a rod problem to a move one disk to a rod problem. And you can imagine that's pretty trivial, right? If I just had one disk here, like just the red disk and the other one's not below it, and I said move it to a rod, then that's super easy. You just move it there and you're done. So the goal with this is that we're going to do some recursion. We're going to recurse twice. In this case, we're going to recurse once on moving the tower to the open rod. We're going to recurse a second time afterwards to just move it to its final destination. And then we have something here that's not recursion, where we actually just move it to the big disk to wherever it needs to go. Right, so we have two cases of recursion. Our reduction operation is reducing the number of disks that need to be moved to a specific location. So we're decreasing this from a disk tower of 3 disks to a disk tower of 2 disks, which is easier to solve, and then that will be reduced down to a disk tower that's eventually 1 disk, which is trivial to solve because you just move it to where it needs to go. And then we have a base case, which is also that 1 disk. So the reduction operation is approaching that 1 disk, and the base case is that 1 disk itself. So you can see we have all 3 of those aspects that we talked about last time: the recursion, the base case, and the reduction operation, but they're not strictly just arithmetic operations like addition and subtraction. It kind of is, you'll see in our code here, but it's reducing the size of a tower. So I've gone ahead and coded this up really quick here. And so you see the main function's really nice looking. It's just a call that says solve tower of Hanoi. And what I've done here is I've written a recursive function. I put some explanations so that you can see this when I post it on Canvas. But what this is going to do is it's going to check for our base case. If the tower size is 1, then that's trivial. Just move the place from the source to the destination. So our function, I guess, takes 3 parameters. It's the source, so the rod that we want to move from, the destination, the rod that we want to move to. So our main goal is to move from rod 0 to rod 2, and then the size of the tower in disks that we need to move to our final location. And so if we have a tower size of 1, that's trivial. You just move it there. And then we need to do our actual recursion. So first things first, I do a calculation here to find how many, or sorry, not how many, but what disk the unused one is. So a trick for this, if you're ever looking for one thing and you have a bunch of other ones and you're just looking for like where the one missing is to do a sum. So you notice I did 0 plus 1 plus 2 here, which is the sum of all of these rods. So I did 0 plus 1 plus 2 equals 3. And since we have 2 of the rods and we're looking for the third one solution to find whatever the last one is to simply just subtract by whatever 2 you have. So in the case of our initial call, 0 is the source and 2 is the destination. So if we subtract by those 2, you'll notice we get 1, which is the one that's not being used for the source and the destination. Oops. Right, if I'm moving from 0 to 2, then 1 is the one left over. And so you can kind of imagine algebraically that what we're doing is we're subtracting whichever 2 of these numbers are not in use for our source and our destination, and we're left over with whatever the number is that represents the open one. So in the code here, I've done that. I've done 3 minus source minus destination to find out whatever the peg is that's not being used for our source to our destination. And then I have the recursive calls here. So first we are going to move the tower to the rod from the source to the unused one. That was kind of like when we had the small tower before, we were moving the small one to whatever the unused one is first so that we could get the big rod, or sorry, big disk at the very bottom free so we could move it over to wherever it's supposed to go. So we're going to move from the source to the unused, and we're going to move the tower that's on top of the big disk, which is the tower that's one less than our entire tower. We're then going to move the big disk. So I just have it print. I don't have it actually move anything in like class, but it's just going to move the big disk to where it needs to go. That's on the bottom of the tower. And then we finally move the small tower that we moved to the unused rod from that unused rod over to where it needs to go. And again, that's going to be the tower size of -1. So you can see here, this problem seems kind of hard to approach at first, but when we write it recursively, it really is just 3 lines of code and a base case. So if you break it down to a recursive problem, it becomes way, way easier to solve, and the code becomes kind of trivial, even if we do get that performance hit from doing recursion, which we are going to get just in general. You can imagine like doing this with a loop is probably pretty difficult. You need to keep track of all these unused and destination and source, and maybe update them constantly on every loop, and we need to store them in some way because the fact that this tower happens here and then we have another print, it becomes really confusing. So doing this with a loop, pretty hard, but doing it with recursion is pretty simple. And then here I've given a wrapper function, which I just wanted to briefly mention because I know somebody, I think, asked a similar question to what I was trying to go for here last class. And so when we do recursion, we need to give some initial base call to our function where it has knowledge of what it is we're trying to accomplish. So in the context of our problem here, we're always trying to move from the 0th rod to the 2nd rod, the last one. And that's not necessarily something that the person using your function should have to know to be able to call your function, I would argue. So they have to have some knowledge of the fact that it's recursion and some knowledge of the problem in order to be able to call your function correctly. So what I like to do for things like this is create what I just call a wrapper function, which is just a function that all it does is call the initial first recursive call, and it gives the arguments. So here we're saying move from rod 0 to rod 2, and then move the entire tower over. And then you'll see in main that it's just pretty simple. We just say solve tower Hanoi, and it does it. And whoever uses our function can specify the number of disks, but they don't have to know too much about a problem or about recursion in order to be able to do it. And I think that's just kind of an advantage of using a wrapper function. Just go ahead and run this really quick, and we'll verify that it's the same as what we wrote down on that whiteboard. And it ran. So we see 0 to 2, 0 to 1, 2 to 1, 0 to 2, 0 to 1, 2 to 1, 1 to 0. Oh, I'm sorry, 0 to 2, yep, 0 to 2, 1 to 0, 1 to 2, 0 to 2. And so it seems to solve it. And the code we wrote, while conceptually a little bit difficult, is really easy to write, right? It's just like basically 4 lines and maybe a calculation. So recursion might seem kind of strange at first, but when you get these hard problems, it really is very helpful for problem solving. Any questions on what we've done so far? Or why that works? Okay, don't see any questions, but if you have any, just stop me. What I want to do really quick is just talk a little bit about how many steps this takes to execute, and then maybe have a look at the calls that this required to actually do it. Just because we talked a little bit about head recursion and tail recursion last time, and I want to talk about the fact that that ends up being important, like function calls end up being pretty important when we do recursion. So first things first, you might notice that this is 3 moves, and this was solving the problem of 2, and this one was also 3 moves, and that was solving the problem of moving a tower of size 2, and then our whole problem was size 7. So it took 7 moves to be able to solve something of size 3. You can kind of see here, if we have n many disks, let's just say, then if we wanted to write a function with the moves, let's just try to make a guess. So tell me if you see any pattern or if you have any guess as to what this is. If I want to move a tower with 0 disks, that's trivial, that's 0 moves. If I want to move a tower with 1 disk, also pretty trivial, that's 1 move. If I want to solve a tower of 2 disks, we saw that that took 3 moves, and if I want to solve a tower with 3 disks, it took 7 moves. Does anybody notice any power, or sorry, any, no, I might have given you a hint there, any pattern with what this is? And by the way, this is just for fun. We're just going to talk about this so you can kind of get a head start for later CS classes. And it may help if I give you, well, let's ignore this one. But I'm going to give you the numbers that these are 1 smaller than. Do you notice anything about these numbers? And specifically with their relation to n. Perfect. Yeah, I see a private response and a public response, and you guys are both on the right track. So 2 to the nth, right? So 2 to the first power is 2. Actually, I guess 1 more than this would be 1, so that's still 2 to the 0th power. So this is like 2 to the 0th power, 2 to the first power, 2 to the second power, 2 to the third power, and you can imagine that this one is going to take 15 moves, which is 1 less than 2 to the 4th power. And this pattern is going to keep continuing. So we can write this as 2 to the nth power minus 1. So I guess I'll go ahead and erase these now because they are just 1 bigger. So if they're 1 bigger, then subtracting by 1 would get us these answers. And all of these moves are 2 to the nth power minus 1. And so I just want to talk a little bit about recurrence, which is a way that we can kind of show that this works or come up with this idea. And then just kind of consider what this means on top of that. So I'm going to be super informal. I'm not assuming that everybody's taken discrete math so far, but if you have, or you have an idea of what induction is, we can kind of use that to show that this works. So if you consider what we were doing here, let's just say I write a function called m that represents how many moves it takes to solve this. And I say that m is a function of capital N, I'm going to say. Then what we're trying to assert here is that 2 to the nth power minus 1 is how many moves it takes. So one way you can show this is by trying to find how many moves it would take for the n plus 1th n plus 1 many disks that this takes, and to be able to write it in terms of something that we do know rather than just the assertion that we're trying to make. So we're asserting that this works, but we can't really know that unless we test infinitely many disks and make sure that they all follow that pattern. And obviously you can't test infinitely many things. If you're familiar with logic or discrete, then that's trying to prove that all universal quantifier, the upside down A. And you know, if you have an infinite set, that's not really feasible just to show by proof by example. And so one way we can do that is we can consider what we wrote recursively, which is we wrote a recursive call to the size of n minus 1, and then we did a recursive call to the size of n minus 1 here, and then we did one extra move, right? So we're going to solve this problem 2 times with the tower that's one smaller than our current one, and then do one extra move after that. Right? So if we make the assumption that this function works for all cases up to n disks, and we want to prove that it works for the n plus 1th disk size tower, then what we can do is we can say that it's 1, which is that one that we had for moving the one disk, like the big disk, to its location, plus 2 times this function. We'll just say 2 times the amount of moves it took to solve this problem for n plus 1 minus 1. So the amount of disks, 1 less than what we said, right? Hopefully everybody follows so far. And so what I'm going to do is just quickly reduce this. N plus 1 equals 1 plus 2, and then I'm going to substitute this in, since we know that m to the n equals 2 to the n minus 1 for disks less than or equal to n. So because this is less than or equal to n, it's equal to n, then we know that this would be 2 to the nth minus 1. We can work that out a little bit. We get 1 plus 2 times 2 to the nth is 2 to the n plus 1. If you remember, when you multiply things with the same base, you just add their exponents. So this one has an exponent of 1, and this one has an exponent of n, so this would be n plus 1. So if I distribute, that's what I get for that part, and then minus 2 if I distribute it all the way out. And then we can't do anything with this because it has a variable power, but we can touch these, right? So 1 minus 2 is negative 1, and we get 2 to the nth plus 1 is equal to the n plus 1. So what we've said here is that this move thing kind of yields the same formula where the power is n plus 1, and that's our parameter to our like math function here, and it gives us the same kind of form or formula here where it's 2 to the n plus 1 rather than 2 to the nth minus 1 for n plus 1 disks. And it's okay if you don't fully understand this. I just kind of wanted to bring this up so you have a head start on this kind of stuff for 302. But we can show with recursion that it's going to take some amount of steps if we have an idea of how many steps it takes to solve problems that we already know how to solve, like the smaller problems. So why is this important? Like, why do we go through all this and establish that this is 2 to the n minus 1 many steps it takes to solve this? So it's very important to consider how many steps it takes to solve a problem when you're doing computer science, just in general, because the processor speed that you run a problem on will affect how fast your program runs, but it's not always the greatest metric because of the fact that, you know, processors are different amongst different computers. Like, I probably have an average processor, and I'm sure everybody else does here too. But if you're on a supercomputer, then a program's going to run super fast. So describing problems in terms of how long they take to run real time, like seconds, is kind of bad. So generally, the way you describe how fast you're solving problems is this way, where you describe how many steps it takes with respect to how much ever input that you have. And if something is exponential, you know, if you remember from your high school math classes, exponential functions look like that. They just have like a really steep curve upwards versus like linear functions or quadratic functions or whatever. You know, they're both curvy, like the quadratic in that, but you can imagine, if you remember your calculus, that this has a much bigger derivative than this one. This one, if you take the derivative twice, it ends up being 0, right? Or 1, sorry. But this one, if you keep taking derivatives, it's going to have ln, and it's going to take a while and never actually get to like a stable derivative. So this one has like a way bigger slope than that one does. The point being here is if you have something where the amount of steps it takes to solve is exponential, then it's going to take a really, really long time to actually solve that problem. And I put a link in the code here that I think talks about like some lore with this. I just put the Wikipedia article. Just if you're curious about the Tower of Hanoi, and it opened up the GIF. Okay, there we go. And they have some sort of lore here where they said that there was like I think a god named Brahma, that there were a bunch of monks that were moving the Tower of Hanoi, and it has 64 discs, and they were just going to move it, and once they finished moving it, Brahma would make his return. I think that's what I read, and somebody can correct me if I'm wrong. I don't remember the stuff before it. Yeah, so they say something about here too. Yeah, so they say moving 64 discs. And then you can see on Wikipedia they say that's roughly 585 billion years to finish moving all those discs, which is about 40 times the current age of the universe. So when you have these exponential amount of steps to solve a problem, like with this problem, it becomes very interesting to solve because a computer, even though those are faster than monks, I guess, it's still going to take ridiculously long, longer than you actually have time to wait for to solve a problem. So it solved it pretty trivially when we have only 7 moves that it had to do when I type it here, but you'll notice if you went and replaced my code, I put a constant at the top if you want to play around with it. But if you made this disk code even something like 10 or 20, it's realistically not going to finish anytime soon, probably not in the next few days, and maybe not even in your lifetime, depending on how big you make that disk. So these exponential things, because they have such a big curve off, like such a big slope, then they're really important to consider those kinds of problems because you can't solve them in realistic amounts of time. And that goes for recursion or just outside of this. Right, so does anybody have any questions? I kind of just wanted to throw that out there so at least you have an introduction to this before 302, because that's kind of the foundation for part of that course. But when you're writing programs, it's very important to consider your runtime, not in terms of seconds and like processors, but in terms of how many steps it's actually taking you to do the problem. And if you heard in 135 that bubble sort is really bad, that's because it has something. It's not exponential, but it's like n squared, which is not good. And that's why everybody says that one's bad. Okay, fair enough. Don't see any questions, so I'll digress. None of that will be on the exam, but the recursion, I think, at least hopefully shows to you why recursion is nice and serves as an example of where you would actually use it rather than the random one-off examples we did last class. Okay, so let's take some time then to talk about something new. Let me go ahead and close this. We'll maybe do some programming, but let's just talk a little bit about the data structure here. So you're going to have to bear with me for a second. I'm just going to talk about something that seems like it's kind of unrelated. But what I'm going to do is I'm going to create something that we're going to use for the rest of this class called a node. And what a node is going to be is it's just going to be something that holds some amount of data. So we're going to have a data field. This can hold like a number, or it can hold a string, or a character, or a class, or a pointer to a class, or whatever. We're going to have something that holds data and then has at least one pointer that points to other nodes. And so we're just going to have this kind of basic structure here that's able to hold something and then is able to point to something. Or point to multiple things you can do as well. But for the time being, let's just point to one thing. And so the general structure we're going to have for this node, for our code, is I'm going to do something like this. I think this is an example of where template classes would be nice. So say something like template class T node. I guess I need to put class node. And then just generally, we're going to want this to store some kind of data. And then keep some sort of pointer to another node. So I'm just going to say node T pointer. And we'll just call that pointer, or you might see me call it next as well. But this is going to be the class that we're going to be using for the next few lectures. It's going to look like this generally. So just keep that in mind. It's going to have a data field that stores something that you want to keep track of, and then a pointer to another node that just is going to represent kind of like a path that we're going to follow, you'll see. And so I'm going to use this definition for the next few lectures. So just kind of keep it in mind. We've talked about static arrays in CS135 and then dynamic arrays here, if you remember, and we had dynamically sized arrays where we could do something similar to a vector and only resize the array to allocate as much memory as we need, except we had the problem when we had that, right, that if I had an array of, let's just say 3 things in it, so size equals 3, and I fill it with a bunch of numbers, let's just say it's an integer array, count equals 3, then if I want to dynamically resize this, assuming that I'm storing it this way, is that I would have to make a bigger array. Let's just say it takes 5 things, copy everything over, and then I'm able to start putting things into this like unused space, right? So we end up making the size a little bit bigger and then transferring everything over. And we said that this was good for data management because we only use about as much data as we need, or about as much memory as we need. But it came with the performance hit because we have to copy things over whenever we run out of space, and we have to do a memory allocation with the new keyword. And so there's a little bit of a performance hit when we do dynamic allocation versus static arrays. So with these nodes, what I want to offer first is a way to be able to do this with nodes and avoid at least the copying over part of this that we have, and only do it, really only dynamically allocate like one at a time. So the way we're going to do this is with a thing called a linked list. And what a linked list is just a bunch of these nodes with whatever their data is, and then a pointer to whatever the next thing is in the list that we want to keep track of. So all of these are just going to point to each of the next nodes until we reach the end of the list. And the way we're going to signify the end of the list is with the null character. I'm just going to use character, but you'll use null or null pointer, and that will signify that we've hit the end of the list and that it's pointing to nothing. So the advantage of this is that if I want to put something into this linked list, like push back something, let's just say, then it's pretty easy, because if I want to add something new to this list, all I have to do is make this one at the end point to whatever new stuff I want to put in, and then just make that one point to null, right? So this ends up being a little bit easier than a dynamic array in terms of adding things, because we don't need to constantly resize. We just add a node to the end of this list of things that we have. But it does come with some downsides, which we'll see later. Okay. So this is just our general structure so far. So we need to define a few different actions. So this was our add. We added something to the end of it. So let's actually kind of split this up a little bit. Over here. So I have a list. Let's just save two things right now. And let's talk about what we need to do in order to add something to it. One thing I should mention too is we're going to keep a pointer called a head pointer. I'll just call it head. That points to the beginning of this list. That way we know where it starts. And then we can kind of follow it along as we go to reach whatever it is that we need to access. So let's say I want to add something to this. I should probably use a better word. Let's just say insert. Insert is the common name for this. Then what we need to do is we need to make the new node. Let's say I'm adding the number 4 to the end of this list. Then what I need to do is add the new node that stores that number 4. So this is 3 and that's 2. And then I need to make the current end of the list point to that. And then I need to make it null at the end. So we're always going to end these lists with a null, just as a way to cap it off. You need to do 3 things if we do an insert, which is make the new node, and then in any order, basically, we just make the old end of the list, which I'm going to call the tail. So if this is the head, I'm going to call this the tail. Let's make the old tail point to it. And then we make it the new tail by making it point to null. Essentially, we got to do these 3 things. So this allows us to just quickly add things to the end of it without having to resize like we did with the dynamic array. Does anybody notice an issue though with the way that we're adding things? Not in terms of like bugginess, but is there a problem that we're going to run into by inserting this way versus a dynamic array? Like, is there a downside to this? So I guess I'm gonna say, if we consider the dynamic array that we had before, the way we inserted was we didn't have to necessarily go to the end, but we kind of just threw whatever it is we wanted to put into the array just straight in there, right? So if I wanted to go and just put the number 7, I just go straight to that location and put it there, because everything is just right next to each other in an array, right? So you can just jump straight to wherever you need to go and put it in to the location that it needs to go to. When we do this linked list, what we end up having to do is, as far as this structure that I've done here, we're only keeping a pointer to the head of our array or of our linked list. So if we need to do an insert or do anything in this linked list, we actually have to like jump around because these aren't located right next to each other. So if I actually wanted to get to the end of this list, I actually have to go start at the head and like work my way to the back until I get to this last thing. And then I'm able to insert whatever the tail is every single time, assuming I don't keep some sort of pointer to the tail. So one issue with a linked list is that it's going to take a really long time to do simple operations, at least compared to the dynamic array. And if we kind of go back to those functions that we were talking about, like amount of steps it takes you to solve a problem, this one's going to take you n many steps, where n is the number of things in our list, whereas the dynamic array only took 1 step, which was just go to that place and put it in and resize if you have to. So while this saves some time every once in a while, because we don't have to constantly reallocate space, it is generally worse because we have to do this weird traversal to access things. And you're going to see that as we do some more operations here. So this is just our insert. It has that problem. If we did some other things, so we just need to consider a few things that we need to do when we're using an array in general, or any kind of like list structure. So we need to be able to put things in, which is what we did. We did insertion. We need to be able to get things that are in our list, and we need to be able to remove things from our list as well. So we've done the insertion. Let's go ahead and do the deletion. Actually, before we get to that, let's go back really quick. I want to talk about one special case really quick, and that's if your list has nothing in it. Since the end of our list always points to null, and we have a head pointer that points to the beginning of our array, our list, then if you ever have an empty list, the way you're going to have to do it is you're just going to have it point to null, and that ends up being your empty list. This means it's empty. It has no nodes in it whatsoever. And if this is the case, you're going to need to actually do some checks on some of these. So let's just double check that that works with our steps here. We say make the new node. Okay, we make it. We make the new node. We make the old tail point to it. Well, this is the tail because it's nothing, so we just make this point to it. And then we make its pointer point to null. So it generally seems to work, at least if we keep track of where the tail is. So there's actually nothing special about insert as far as our list goes when it comes to an empty list, but you'll see it does end up affecting some of our later operations. So we're about to talk about access. Access is pretty easy. So I'm going to call it lookup. That's generally the name we use. So insert is for putting things in. Lookup is when you want to grab something. So we're going to consider the two cases. One if we have an empty list, and one if we actually have like a real list. So we'll do the real list first. If I have one of these list structures with all these nodes, and this is some stuff that's in there, and then this points to null, and we have the head. Then if we want to get something, so let's just say this is like the 0th thing, this is the first thing, or the second thing, then it's actually pretty easy. So let's say I want to look up and access, so let's just call it get for now. We're going to do two different ways here. Let's say I want to get the first thing, then that would be this node right here. What we'd have to do is we'd have to start at the head and work our way until we get to this first node. So it's actually pretty simple. It's not too hard to do this one. One thing we can note about all of these nodes is that whatever their index is the number of times we've followed pointers in order to get there, aside from the head pointer. So if I look at just this 0th element, then I've had to follow 0 pointers to get here because the head pointer just points directly to it. If I want to go to the first node, then I would just start at the head pointer, follow this guy, and I would end up at my first node. So I followed 1 pointer to get to the first guy. And then if I wanted to get to the second guy, I would follow this pointer, followed by that pointer, which is 2 pointers. So to get to the second element, you need to follow 2 pointers. If I need to get to the third element, I would follow 3 pointers and 4 pointers, and etc. So our general strategy for this version here is just start at the head, and then follow the pointers. I'm just going to say n, for n being the number that we want to get the index at. So this one's pretty easy. We just like follow it n many times, and that's pretty simple. Just start at the head, which is where we always have to start, and kind of work our way back. Let's say I have a more specific array, so I just kind of like have been scribbling. But let's say I have a different array where we need to access it, and it actually has like real contents in it that you can see here. So let's say this is an integer linked list, and this takes a 4, a 7, and a 9. And we'll say that we want to do a linear search through this, similar to how you do in an array where you search through it for a specific number. I'll call this one lookup. And I want to do a lookup where I look for the number 7. Then we actually have to do a little bit more work if this is the way that we're trying to look up things in our linked list, because we actually kind of have to like check what is in each of these rather than just blindly following the pointers until we get to where we need to go. So say if I was looking for the number 7, then what we would do is we would start at the head pointer, and we would need to check each individual node to see if it's the thing we're looking for, and then if we find it, we would end up just returning it. So here we would check, is this the number 7? Well, no, it's not. And so we would go and we would follow the pointer, and we would check the next thing, and we would say, is this the number 7? And yes, it is. And so we would return something to signal that we found it, either just like a Boolean true that says, okay, we found this, or something like the index that we found it at so that we could use it with the other get function that we just wrote, or we would return this pointer that we found right here. But it kind of depends on what we're looking for, but we would do something similar. We would start at the head. We check, is this a match? Is this the thing we're looking for? And if not, then go to the next one. So that's our general search technique for this one, is we need to go to each node and then kind of follow along. Right, and just so we cover all bases, if we have an empty list where the head is just pointing to null, then we can never find anything in it regardless. So when you write a function like this, I suggest you make sure that the head is not null before you do any code, because if you have an empty list, then you can't traverse it. There's no like pointers to follow along in order to get anything else. So we would just bail or return out of the function immediately if this was the case. And we'll write the code for this eventually. I'm just kind of trying to go over the concepts. But if we write any of these, generally we'll want to check this case of, is the list empty, before we do any code. It's just a good idea in general. Okay, so we've got lookup, we've got insert, and the last thing we need to be able to do is be able to remove something from our list. And so this one, I think, is the one that's the most difficult. We'll just get it out of the way immediately. If I have an empty list where it's just a head pointing to something that's just null, then that's trivial. You can't delete something that's not there, so that would be nothing. I'm going to call this function remove. And remove and lookup are very similar when you do data structures like this. It's just that the remove needs to find the thing and then take it out. So it's really, they're doing the same sort of thing. It's just one returns whatever you're looking for and the other takes it out of the list. Or whatever data structure you're using. We're doing lists here. So let's say I have another linked list and I want to remove something. And this one's a little bit harder than the other ones that we've been doing. So let's say, again, this has some sort of numbers in it. Then let's say I go and try to remove the number 4. What we need to do, similar to the lookup, is we need to find where 4 is by just following all of our pointers. So we start at the beginning and then follow our arrows until we find it. The general setup is pretty much the same. So start at the head. If we didn't find it, try the next node. right? So if I'm looking for the number 4, I would check, is this for no, move to the next one, is this for yes, and then we can actually try to delete it. And then we needed to actually do the deletion. So else delete. And so this one's where it becomes tricky. So I know I'm writing the word delete, but don't literally write delete. We are going to do that, but don't actually literally write just delete because it's going to be an issue. So consider if I just went here and I just deleted this straight up and didn't do anything else, which we totally have the option to do since these are pointers that we have to these nodes, right? Then I have an issue because if I move something in the middle of the list, then this part right here is still pointing to what was deleted. And now everything that came after that number, the rest of the list, we've lost access to it because there's nothing pointing to it anymore. We deleted the pointer that was pointing to the list that was to the right of it. And the thing to the left of it is not actually pointing to it. So we need to fix that. So before you delete any sort of node in a linked list, any sort of element, what we need to do is redirect this pointer to go around it. So we'll see this when we actually write the code, but what I'm going to say is we keep track of the last node we visited. So what I'm going to do is keep track here with some sort of variable that points to the last one that came before whatever we're trying to remove. So the 3 came before the 4 here. And then what we need to do is we need to update its pointer to point to the thing that comes after this. So in other words, we need this pointer to get copied over to that pointer. And then we can delete it because we've fixed the problem, right? If we kind of consider this, we've like removed this node from the list so that this now like redirects correctly over it to the rest of the list that came after it. So it's now safe to completely delete this. So what we'll need to do is keep track of the last node, set it to point to the list after it. And then we can actually just delete the node and cut it off and kill it. So just some caution here. Make sure you're not getting any memory leaks. Make sure you redirect this pointer around your nodes if you're going to remove something. Now, there's one extra issue we have to consider here, which is if we are deleting from the head. So if we delete from the tail, it's actually totally fine. If we kind of consider what we just said here, we keep track of the last node, set it to point to the right of the list. So if instead here I was trying to delete the 7 instead of the 4, oops, I don't know where that all went. Okay, well that's fine. If I was to delete something at the end, let's just say we have the same list, 3, 4, and 7. And I wanted to delete the 7. Then what we just said still works. So if I want to remove this, all I have to do is make this pointer point to whatever comes to the right of 7, which in this case is null, and then delete the 7. And that ends up working because once you delete the tail of the list, whatever came before it is now the tail of that list. It becomes the end of the list. And so if we just have it point to the null that this one used to be pointing to, then that's totally fine. So tail deletion is safe. Nothing special there. We don't have to do anything extra. We can just reuse the same code. But head deletion is a little bit different. Again, and we'll say we have some kind of list like this. I'll just do two things, 3 and 4. And then we have a head pointer to this. Then our strategy was have the head pointer, like the last pointer, point to the next object and then update its next. But when we do a head pointer, there is nothing that comes before this, right? There's no node to the left of this that we're going to be able to redirect and make to that thing. So there's one special consideration that you have to do, which is if we're deleting the head, then our goal is to move this to point there now, so make a new head, essentially. Deletion has one extra thing that we need to check for, which is this, compared to all the rest of them, where we can kind of get away with doing whatever we wanted, and the code works every single time. There's nothing special for an empty list for this one, but if we are deleting the head, then all we have to do is update the head to point to the next thing, and then we can actually delete the thing we are looking for. What the hell if I could spell? Then all we gotta do is update the head and then delete like normal. So it's just slightly different game plan because our previous solution to this was we had to keep track of whatever came before the thing, but in case of the head, there's nothing that comes before it, so that's just a special case, or an edge case, you might call it. So just something to be aware of. Okay, so I think that about covers the 3 operations that we can do with a linked list. So we can either code this up, or I realized I forgot to mention something about the recursion tree. So we got what, like 15 minutes left? I'm not thinking we can code this up in 15 minutes. So I'm tempted to just talk about the recursion really quick, if that's okay. And then we'll code this up next time, I suppose. Or we can just at least start on it. So let's try to talk about the recursion really quick. I'm sorry to swap topics. Nah, we'll do the recursion next time. Let's start trying to code it, I guess. Let me open up a new project. Because I feel like it'll at least be easier to remember if we do it this way. Okay, so let's go ahead and just try to at least write the beginning of our linked list class, and then I guess we'll just finish it next time. Already exists in the project? Oh, that's the name of my main, huh? We'll just call it list, I guess. And we'll do a header. Okay. So let's just write a generic list class. I'm going to do this with a template because that way we can store anything in it. And we're just going to have some generic type called t that it's able to store. I guess this is a good reminder for templates too. And what we need before that is we need a class for the node, which is also going to be a template class because we want the node to be able to store anything. So we said our general structure for that is we're going to have some sort of t called data, whatever type that is, and then we're going to have a pointer to some other node of type t that it holds, and I'm just going to call that next for now. So just whatever the next thing is in our linked list. And then all we really need to keep track of in our list is a node pointer to the head. And that's really just the bare minimum that we need for this. You can add some extra nice features, like you can keep a pointer to the tail so you don't have to go through the whole array every single time, or you might keep track of like an integer for counting it or something like that. I'm just going to do it this way for now. So let's write a few functions. We'll write a constructor. We will write a insert function, which will take a t object and put it into our list. We'll do a lookup function that looks up something. Just call it object. And then we need to do a remove or deletion. I'm sorry, that's the correct term. Deletion. And we'll do a t, and then we'll just call it object as well. And actually what I should do, I know I wrote this as a class, it's actually considered common to do a node as a struct, because the only thing that's really going to be able to use the node anyway is the list class. So I'm just going to do this as a struct so that everything's public. It'll be easier that way. And we'll go ahead and write this in here. So include list.h. Oh, right. When we're doing these, we actually need to put this first. So you need the template every single time you write one of these. Because, again, it does, if you remember when we talked about these template classes, how many ever weeks ago, it just fills in that variable t with whatever type it is that you're actually trying to use, so like integer or float or whatever. So you actually do need to put that every single time so that it knows when you're doing these declarations, because it is just going to copy and paste code. You do this. I'm not exactly sure why that's an error. Explicit type is missing. We shouldn't need an explicit type. Oh, I need a return value for these. Did I not write that in here either? I didn't. Whoops. So insert, we'll say is void. Lookup, I don't know. We'll just make that return a node pointer. And deletion, we will have it return void. Or maybe a bool. I think bool's okay for these two, just whether or not you're able to successfully do it. Okay, so let's go back here. Deletion, we said we want to make void. Lookup, we'll have it return a pointer to whatever node we found, and then this one will have the void as well. Okay. So first things first, the constructor. We said that if we have an empty list, that it's just going to be something that's pointing to null. And so the constructor is pretty trivial. We just make the head point to null, and that's it. So this should be okay. Just making that it doesn't get angry at me. I think it's fine. So that one's pretty easy. The insert, we're going to need to go all the way to the end and then add the thing to the end. And so we're going to use this code pretty much for every function that we write for these, which is just going to be the traversal of this. So the way I usually do it is we create a pointer, and this is going to represent whatever pointer we're currently looking at in our linked list as we traverse from left to right. I'm just going to call it current, and by default, I'm going to set it equal to the head. And so the way I check these is I generally say while current does not equal null. And I like this check because of the fact that if the head is null, then when we set it to the head at the very beginning, then it's just going to immediately skip this while loop. So if we have an empty list, this just doesn't execute any code, which is kind of nice. But this will also, with what we're going to write here in a second, it's going to update current to like follow the pointer over time. And so if we hit the end of the list as well, then it's going to hit null that way too. So this while loop covers both if the list is empty and when we run out of things to check in the list. Okay. So what we'll do here is we'll keep track of current, and what we'll do is we'll set it equal to current sub next. Actually, I guess there's probably a better way to do this with this one, but we'll check it inside the while loop. There's multiple ways that you could do this. The insert's, I guess, a little weird. But this part right here is going to allow us to traverse the array. So what I'm going to do is I'm going to overwrite our current pointer to a given node and make it equal to the next, which is this arrow here. So what that effectively does is if we start at the head right here, then it's going to point to this. And then over time, I don't know why my pen's not working anymore, but over time it's going to make it point to whatever the next pointer is for the current point that we're, the node that we're pointing at. So to point to the head, and then if it doesn't find anything, it will follow this to the next one, and if it doesn't find anything, it'll follow to the next one, and if it doesn't find anything, it'll keep following it. So this kind of allows us to keep updating it so that it's pointing at each successive node in our list if we update it this way. Okay, so that will essentially work for us. I'm actually just gonna, I'm gonna do this as a separate case. I'm gonna use this while loop for the rest of them, I think, but I'm gonna check if the head is null. I suppose we have to do that anyways, because if we're inserting something into a list where the head is null, we have to update the head as well. So I think this is probably a better way to do it. While we're doing this, let's go ahead and make a new node. The first thing you generally want to do when you do insert in general is just make a new node to insert. So let me actually go back here and write the constructor really quick. Node t, and we're going to make it take a t, call it the data, and we'll set this data equal to data, and then make the pointer equal to null. This way we just have a node that whenever we make one, it will store whatever it is that we're trying to store at that node, and then just make it point to nothing by default. So what we'll do is we'll make a new node. I'll just call it new node, and we'll construct it using the data that we're using to make it. So if the head is null, that means that our list is empty. And that's pretty easy. All we have to do is make the head equal the new node. And that's it. We just gotta, if we have nothing and we're inserting one thing, then we just gotta make the head point at it. And I'm going to say else. And I'm going to make this current next instead. Put braces around that so it's a little easier to read. And then current sub next equals new node. So to explain what this does, if our list is empty, then just set the head equal to the new thing. Else, if the list is not empty, then what we need to do is we need to keep traversing the list. So start at the head, which is what we set current to. I suppose I should move this down here as well. So start at the head, make that our current node, and then while the next pointer is not null, so while that's the tail pointer is not the one we've reached, then we just need to keep traversing by following those pointers over and over again until we actually do reach that tail, which is going to break this statement here, because the next of the tail is always going to be null. That's how we signify the tail. And then we just set it to be the end. In fact, you know what, in hindsight, no, I was right originally. That works without it. We don't need a special case. This is always correct. Because if we set the current to head, the head's next is equal to... No, I'm sorry. No, I was... I keep backtracking. No, that's right. We do need to check it separate. I'm sorry. So we have a question, how does calling next move to the next node? And so the reason that works is because next is always this part right here. So the anatomy of a node is always the data that it's storing, which is the thing that I'm always going to draw on the left here. And then the next pointer, which is always the pointer that points to the next object in it. So those are the two fields that it has every single time. By setting it equal to the next of the current one, it's going to end up pointing to the whatever the next one is. So if I start here and make this my current, just say cur, then the next of current is that pointer, which points to that guy. So by setting current equal to current next, then it's saying set current equal to this pointer, which is pointing to right there. And then if I do that on this one, that'll have it point over to that one. So it allows us to just kind of easily do it with one single statement. Okay, cool. So I guess that's probably a good stopping point. We've got about a minute left, so I don't think we can do anything super important. I'll see what everybody's responses are for that stream, and we'll try to do that this weekend. What was the other thing? I'll hopefully remember next time to show that function call tree for the Towers of Hanoi, because I think it's kind of just nice to know about. And I guess that's about it. So I will see everybody next week. And if you have any questions, I'll stick around and feel free to ask questions about assignments or topics.